Good day, everybody. Today I want to look at a result that lets us know that there is no measurable set on the real line such that it'll equal the measure of that set will give half the measure of every interval, or more precisely, there's no measurable set E such that the measure of E intersect an interval gives half the length of the interval for every interval. So proof's right here. It uses the result that if the integral over every interval, integral of f over every interval equals 0, then f must be 0 almost everywhere. So as long as we have this result, then we can easily prove this. You just if there was such an E, you can set f to equal 1 for all x in E, f equal -1 for all x in E complement. So then f is 1 or -1 everywhere, or f is 0 nowhere. You can write f as characteristic E minus characteristic of E complement. And well, then the integral of f would be 0 for every interval, right? If there was such an E. But if the integral of f equals 0 for all intervals, then f would be 0 almost everywhere. Contradiction. Get that? So if E intersect AB is half the length, then I didn't know if it needed to be shown, but then, I mean, since these are disjoint sets, E and E complement, these are disjoint, their union is AB. Oops. Their union is AB, and they're disjoint, so their measure of each set then would give the measure of this set, which is B minus A. And this set, we're assuming, is 1/2 the length, so is this one. All right, so E and E complement would both give you half the length of the interval. So there can't be such a set. So that's the proof. If we wanted to look at the proof of this, I did for bounded intervals. Notice our function is bounded. Just a quick guide for all the things to get that top theorem. First, we would need to show that every open set is a countable union of disjoint open intervals. So G is open if and only if G is a disjoint union of open intervals. I should say a countable disjoint union. It is countable. And you can look at, say, the outer measure. It's the inf of, essentially it's the inf of open sets that contain your set E. So that'd be the outer measure of E. And so if, however, G is made up of disjoint open intervals, then the measure of G would be the sum of the lengths of those intervals. And if E is measurable, then for every epsilon greater than 0, there's an open set G. So E is contained in G, and the measure of G minus E will be less than epsilon. So you can always give me an epsilon, and then I can find a G that'll cover E, and then what's extra, that measure of that will be less than epsilon. So those are some preliminaries. And then here's the proof then I would need. So this is the proof I would need. It's actually true for as long as f is integrable, but bounded is a little bit easier. So if the integral of f is 0 for all intervals, then f must be 0. And first note that if the integral is 0 for all intervals, a, b, then it's the integral of f over any open set would be 0, because G is always some countable union of disjoint open intervals, and the integral would be 0 on every one of them. So we'd have that result. Now, if you give me an epsilon, and since f is bounded, for my f I needed, f is bounded by 1, but let m equal the sup of absolute value of f, then set en plus to be all the x such that f of x is greater than or equal to 1 over n. And then en plus the set of x such that f of x is greater than 0. And for each n, pick the open set gn plus, so that en plus will be contained in gn plus, and then the measure of gn plus minus en plus will be less than epsilon over n divided by n plus 1. All right, so all of these are given ahead of time, so we can find the g that'll be satisfy that condition. Then the integral of en plus of f, well, f is going to be bigger than or equal to 1 over n on this set, so this integral is greater than or equal to 1 over n, right? That's a lower bound for f on this set, 1 over n. And then this integral will equal the same integral, then plus and minus the same thing. But these are all, well, these are disjoint, gn minus en plus and en plus. So the integral of this sum is actually just going to be the integral over that open set. And then, you know, f could be negative here, but we'll just bound it by the absolute value of f there. But then I even bound it by put the absolute value on the inside. Right, so this integral will be 0, because over every interval, so over every open set, integral of f will be 0. And then by my choosing of gn plus, this will be, the measure of this will be less than epsilon over n times m plus 1, and of course f is bounded by m, absolute value. So this will be less than epsilon over n. So if you go to the beginning and the end, 1 over n times the measure of en plus is less than epsilon over n, multiply by the n's, and you get the measure of en plus is less than epsilon. It's true for every epsilon greater than 0, means the measure of en plus must equal 0. And, well, that's true for each n. So the measure of en plus is 0 for every n. So en, or e plus, which is the intersection of all the en pluses, right, just wherever f is greater than 0, that will have measure 0 as well. In fact, it's the limit of this, of the ens, but they all have measure 0, so the limit of 0 is 0. And similarly, you can do it with en minus. It's probably best to work with negative f and just mimic the top. Right, so negative f would be positive where f is negative. Anyway, so where this set of x where x is less than 0 or negative x is greater than 0 has measure 0. So f is 0 almost everywhere. So that's what we wanted to prove. Again, it's actually true as long as f is integrable. I kind of just needed absolute continuity of the integral right here. Just a little easier to prove when f is bounded, which is all I needed for what I did today. So that's the result. There's no measurable set so that it can give you the measure of half the interval for every interval when you intersect it with that interval. All right, so hope you enjoyed that. Thanks and have a good day.